Welcome to our class. Special topic: light, nature of light. We're bathing in light. Think about your everyday life experiences. But what is the nature of light? What's the physics of light? What's the explanation behind light? With your own words, please try to give me your understanding. Shining, yes, something which shines, something which we see. In one way it's so common because we rely so much on sight, but in another way it's so deep to answer the questions. Astronomy, probably first of the sciences, for a good reason. Being amazed by the sky, trying to make sense of what we see, try to make sense what light is. Why do I see something and some parts are dark? What is the explanation? As usually we start from the Greeks, and it's common to associate a god, a good god. What? Light, warmth. Life depends on light, with the nature of light, but it's not really an explanation. The first explanation, please read this. Tell him how you think. Maybe. Yeah, it's poetic and it's meaningful, but is it correct? Vote. It's a big class, so I'm looking at the results. Most of you say it's incorrect. Why? John? If you close your eyes, you're going to keep that fire inside you. Or, obviously, if we are in a perfectly dark cave or room, we're not going to shoot from our eyes light. Common misconception. Many kids believe that our eyes are sending light, and that's why we see. Not correct. But how do we know what's happening out there? Can I smell the universe? Can I taste the moon? Or a galaxy? Beautiful picture of Saturn, Cassini mission, suicidal right now. We talked about this, passing through between the rings and the planet. Can I touch Saturn? I'm left just with one sense, unless I have those amazing pieces which fall out of the sky, called meteorites, fragments, chunks, as old as probably the solar system. Yeah, we've been on moon, retrieved some hundreds of pounds of rocks. But that's nothing when you think about how big the universe, the galaxy, and then billions and billions of galaxies. Who is the mailman? Very good. Light. Now you understand why light is so important. It carries information. No FedEx, no overnight delivery, no UPS special, just one service, one speed in vacuum. For a long time, people thought that light propagates instantaneous, because in our everyday life we don't really see that light. Light needs a time to propagate from point A to point B. I can see that for a sound, see a game in the distance, people hitting the ball, but I hear the sound later. Not happening for light in our everyday life experience, unless you use astronomy. That fantastic light, 3 times 10 to the 8 meters per second, 300,000 kilometers per second. It's so fast for us, but actually the universe is so big that speed is actually showing us a universe from some time ago, depending where do I look, solar system, galaxy, other galaxies. We acknowledge today that the speed of light is very fast for us, but we don't travel at that amazing speed. That's why, think about Einstein. He asked himself, what would I see if I run parallel to the beam of light and I look at the beam of light? Yes, that's headache. I'm not going to give you the answer, but he managed to answer by making a revolution in physics, introducing special and general relativity. We are not used to run that fast. So what is important in astronomy, but not just astronomy, having big, big eyes. I'm not going to be able to hear, no ears, no nose, no fingers to touch, no taste, but eyes. Information is brought to us by light. And I start the class by showing my students something which is in a garbage bag, but it's much more valuable. We kept it a mystery. Now maybe it's time to reveal it. What do you think it is? All my students are saying, oh, it's a telescope. It happens to be correct. It's a telescope. In this case, a solar scope. But I call it actually a bucket for gathering light. And even more than that, a time machine. Because light needs time to propagate. What we see, especially when we use a telescope, is stars, planets, galaxies from years, hundreds of millions of years ago. Moon, 1 second ago. Sun, 8 minutes ago. Closest stars, few years ago. Closest to us, 4.2, Proxima Centauri. We already defined in the first chapter what means light year. Remind me, distance traveled by light with that fantastic speed in 1 year. Our galaxy, which is maybe just a grain of sand on a really long beach, which is the universe. Our galaxy is 100,000 light years one side to the other of the disk. So looking farther and farther means going back in time. Andromeda Galaxy, 2.5 million years ago, our ancestors, Homo habilis, were starting to use tools at that time, and we see that galaxy back. So yes, a telescope is a time machine, which encourages you to have big eyes, and yes, a telescope is a big eye. But what's the nature of light? In many instances, light behaves like a wave, like sound, earthquake, mechanical waves, ripples on the surface of the water. And I will try to show you an experiment in which, as you have a big boulder in the middle of a stream, and water has to pass around, we can, I'm gonna turn the lights off, we can have a laser which is passing, you might not see, maybe you see, there's a follicle over here which I donated for the purpose of science. Now I'm gonna shoot a laser through it, and guess what? What do you see? Very good. Ripples. It's called an interference pattern, but we can call it simple light ripples around my hair follicle, as if water ripples around an obstacle in the stream. We can even make it more dramatic. Why not? I keep on forgetting that when I'm closer, I should speak a bit on a lower tone. Okay, so I think I got it. Interference pattern. Light is rippling just because now it's passing through several slits. Each slit has a width which will create this ripple, but in the same time it might also ripple because it's passing in the same time through 2 slits, 3 slits. So it appears the light might be a wave. But some people claim it's a particle, flashlight, a mill inside a bubble. I cannot blow air to make it move. I can tap on the table to make it move. But I'm going to shine the light and see what's happening. And what do you know? I can push objects with the light. That's actually future exploration. Yeah, you can have a sail, and by using the light coming from stars, you can push yourself and accelerate, because light can also be regarded as being a stream of particles called photons. So which one is which? What is light after all? It carries obviously information encased in the energy, but is it one or the other? Who's going to answer that is quantum mechanics. It's both a wave and a particle. Photon which has a wave associated to it. So you need physics. I encourage you to take a class to understand better the nature of light. If we take the wave nature of light, the best way we can classify the light we see and we might not see is by using, this is a wave, the smallest part which can get replicated and create the whole wave, called wavelength. If I clone this, I'm going to have the whole wave. This distance, I should call it with a d, as we know distance is speed times time. But for your entertainment, astronomers decided to use the letter lambda for measuring the wavelength. So I'm going to adopt this, not any distance, the distance light travels in one cycle. Usually we call v c, speed of light in vacuum, and the time is the time for one cycle, which is called period, or the inverse of it, which is called frequency. Period measured in seconds, frequency, how many cycles per unit time, measured in inverse of seconds, hertz. So, yeah, they are inversely proportional. This wave, tell me, is compacted, which means the wavelength is very good. Short, but what can you tell about frequency? It's high. And that makes sense, inversely proportional. Obviously, more frequency, think about being in a boat and waves coming and rocking your boat every second or every just 10 minutes. It's much more energetic transfer of energy if you have high frequency. So yes, we will associate frequency with energy. Light is much more than what we see. Tom? Sure. Very good question. Well, why is that, said Tom. Why don't we see everything? Which might be good. Who will answer? Let's keep the mystery. Let's think about it. But what we see is called the visible part. The whole palette is called spectrum. Visible part of the spectrum. 400 to 700 nanometers, or you add a zero, you talk angstrom, 4,000 to 7,000 nanometers. But we don't see those numbers. What we see is actually, very good, Kelsey, color. The eye, and together with the brain, decode the light, which has the nature of a wave. It's a special wave, not like sound, electromagnetic wave. I'm not going to go into that. We're going to keep it simple. We'll decode the wavelengths in terms of colors. So what we see, probably I can, without switching the lights, I can show you on sides. You have to look on sides. It's much more faint, but I can see the light passing through a prism will spread out into the component colors, which is called, rain colors of the rainbow, or the visible spectrum. Why is that? Well, I don't have natural light here. What I have is a laser. How would you call this? Correct, reflection, so that's a mirror. Very important for understanding how telescopes are built. Spherical mirror, spreading away or gathering the light. This is convergent, divergent. Well, what's happening when light passes through? How do we call that, James? Refraction, very good. Well, it happened, and you can see here refraction. This can be a thick lens, or this, very important. Yes, focal point will be very important. What happens when light passes from one medium to another, and it bends, different wavelengths bend in a different way. That's why the light will spread into the component colors if you force it to pass not once, but twice. Which is why we see the rainbows. Instead of the prism, you have the droplets of water doing that. This is called the whole range of the electromagnetic spectrum. Let's call it simple light. How tiny? Why? Why Mother Nature limited us in seeing such a tiny window? Why don't we see more? Very good. Kim is saying, maybe because we live on Earth, evolution, adapting. Yes, you can even help me by adding this Earth, this size, this atmosphere, those gases, and you would be absolutely right. Coming back in a few seconds about that, this graph has increasing frequency, which corresponds to decreasing wavelength, inversely proportional. Visible spectrum beyond violet, we have UV, X-ray, gamma rays, red, below red, infrared, microwaves, and radio waves. The same, giving you an idea about size. Yes, we live on Earth, that's why. Our atmosphere is a buffer. We're happy to have the magnetic field. Thank you, magnetic field. Why? Sure, solar wind, stream of particles. First shield, second shield, atmosphere. How would I adapt to something which is not raining down to me. What's raining down is that part of the visible spectrum are also radio waves. We have to go really high with the airplanes to get infrared, or we need satellites, which is good because this is the energetic part of the spectrum in order to see X-rays, gamma rays. The same diagram showing you the depth at which light can actually rain down. So it's good for us that we need satellites or fly high-flying airplanes in order to see parts of the spectrum. So if I take one by one, radio waves, we use them for communication. Long wavelength, which means low frequency, which means correct, thank you, low energy. So they are not harmful. So if we would have the eyes to see radio waves, I see classic rock, The Beat, shooting one way, CNN News shooting the other way. We use them for communication. Microwaves, which have from tens of centimeters to below a millimeter, the wavelength, are very well reflected by metals, very well absorbed by dipole molecules like water. That's why you can heat your food in the microwave oven. And they can see through mist or clouds, which is good. But if we keep talking about for the first time the eyes seeing the radio waves, because the wavelength is big, the eye, the dish, the radio telescope has to be big, has to be laying in a depression surrounded by mountains. Why? Very good. You don't want interference since we use radio waves in so many communication. This is one of the few examples of radio dish, West Virginia, which can actually move. Otherwise they are static. They will just move the focal point, the receive grid, to have actually scan a part of the sky. But the Earth itself, as a boat, is taking them to a ride. Arecibo, Puerto Rico. Recently the Chinese constructed a larger dish than that. What do we see? We see low energy things. So molecular gases. This is our galaxy, and we can see the cold stuff, low energy, cold. So atoms can associate and form molecules. An interesting eye in seeing differently. This is a picture of the surface of Venus, which, as you know, is very bright. Now is in the morning, but not because the surface reflects, but because of a really dense atmosphere. The clouds are so thick